Hello, this is the presentation of my ECE561 final project. It's the Universal Wireless Electronic Shifting Conversion Kit for bicycles. Uh, Electronic bicycle transmission have been around for a few years already. They were first introduced for professional racers in 2009, and they are now becoming more popular because they offer more precision, ease of maintenance, and customizability than mechanical transmissions. The history of electronic transmissions includes patent filings for different technologies. So some of the older patents are from 2012, but it still continues to this day. The problem to this day with the technology is that it is very expensive, and generally the components are not universally compatible. So you need to buy components that fit your bike, and some older bikes like classic bikes or low-end bikes are not compatible. There are some conversion kits in the market, like this one on the right, the Archer D1X, which is universally compatible but still expensive. And another issue that there is with this technology is that there's a lot of intellectual property protection, which means that not a lot of companies or people can work on developing the technology. So having an open source system is a plus, and having an inexpensive and universally compatible kit is ideal. So some people have worked on do-it-yourself electronic transmissions in the past. The existing, some of the existing projects that are shown here, and as you can see, all of them are wired. The communication is wired, and the user interfaces are very rudimentary. So no feedback on the gear or any like battery life or any feedback on the state of the system, and rudimentary switches to control. So it can be improved. So I started with the mechanical design of the system, and based on the existing projects and do-it-yourself projects, I discovered that there are two main ways to move the derailleur to change gears. So the first one is using a servo and removing the derailleur spring. So the servo completely controls the motion of the derailleur. The alternative is to keep the derailleur as original and use the original cable, the same steel cable that is used in mechanical transmissions, and just pull the cable with a linear actuator. This means that you're working against the derailleur spring. So what people have been doing to reduce the force required to move the cable is to add a balancing spring. This is based on the spring-to-spring balance, but it's not perfect because for true spring-to-spring balance in a derailleur, you would have to install the balancing spring in the parallelogram of the derailleur, which is not really possible. So this is an imperfect solution, but the spring here, shown in Jesse DeWalt's design, helps a bit to reduce the force required. So this is my design. It's heavily inspired by Jesse DeWalt, but all the components are slightly different. And it includes the motor, includes a slide potentiometer that is used for the position sensing. And it includes all the mechanical components that guide the cable. This one here also holds the spring in place, and there's a guide. And all of this is designed to create a linear motion, a controlled linear motion. For the electronics, we have two different systems because this is a wireless system. So we have the actuator electronic control system, and we have the shifter, which has the buttons and the control unit. So for the actuator, I used an M5 stack Atom stepper motor driver development kit, mainly because it includes a wireless enabled microcontroller, the ESP32, and it also includes the stepper driver. It includes a battery. No, sorry, not a battery. It includes all the interfaces like the USB cable and the voltage regulator. And I also needed a voltage regulator to provide the stepper driver with enough voltage to drive the motor. In this case, a Pololu 15-volt voltage regulator that boosts the voltage of the single cell lithium-ion battery. I also used an accelerometer, an inertial, an IMU unit, a six-axis IMU unit to enable wake and motion functionality. And I used the slide potentiometer that I already mentioned for position feedback. And on the shifter side, I only needed the 5-stick-C mini development kit. It's basically an ESP32 and an LCD display, some buttons, and the interfaces that you need to connect other components, which in this case is only a dual button unit to use for the user interface. So one of the first steps was creating a motor control algorithm. In this case, the control algorithm combines open loop and closed loop control. First, it just uses the open loop control, and it calculates the number of steps required for a gear change based on the transmission and motor specifications. This is hard-coded. This can be calculated for the system, but it never changes. So the motor moves the calculated steps as fast as possible without considering the current or the target position. So completely open loop. And once it finishes the open loop fast movement, it starts a slower closed loop motion in which it reads the current position from the potentiometer, and it compares it with the saved calibration values. So it moves slowly to finally adjust the position until the error is below the targeted threshold. For wireless communication, a communication protocol had to be implemented. The data transmission is based on ESP now, which is an expressive proprietary but free-to-use protocol. Which is similar to Wi-Fi, but without all the overhead and without all the complexity of authentication and connections. So it's a persistent pairing protocol, but it doesn't have all the provisions for ensuring delivery and acknowledgement. So I implemented automatic resend to ensure delivery and successful execution acknowledgement. Here we can see that the shifter, for example, in this case, sends a command and it keeps sending the command until delivery is successful. This is important because the actuator sometimes it's sleeping, as I will mention in the energy management section. So you need to keep sending the command until it's delivered. But delivering the command doesn't mean that it was executed. So when the actuator receives the command, it executes the command. If the execution is successful, it sends a command, a successful execution acknowledgement back to the shifter. But if it fails, it doesn't send the acknowledgement. So on the shifter side, it waits to receive the acknowledgement. If it's received, it displays the success on the screen. In this case, it says command success, but it could be anything like showing a new gear or showing a new state of the system on the screen. But if it doesn't receive the acknowledgement within a given time, it just displays that it failed. Okay, so now energy management. The idea of energy management is to ensure that battery is not drained when it's not being used, and trying to optimize both standby and working condition battery life, while at the same time trying to maintain latency as low as possible, because sleep intervals affect latency. So for the shifter, but energy management is relatively simple. Under normal conditions, the shifter is the sender of commands, so it doesn't need to be awake, waiting for commands, listening for commands. So it can be in the deep sleep state, basically all the time until a user input is detected. And this is important because the shifter has a very small battery. It's 120 milliamp hours, which is a very small energy budget. So even deep sleep can be power hungry. On the actuator side, energy management is a little bit more tricky, because under normal conditions, the actuator is the receiver, so it must listen for messages frequently to ensure low latency and be ready to work. So really, light sleep is the best you can do with the actuator. Light sleep is good because it has very, very short wake up times, and it keeps memory on, so it keeps the state of the system. In this case, the best I could do to lower the power consumption was to use the accelerometer for wake on motion. So the system is either in light sleep, or when it wakes up, the only system that is activated is the I2C peripheral to read the motion flag on the accelerometer. And it only starts the rest of the systems of the microcontroller if it detects a motion with the accelerometer. So as it is shown in the graph. So the sleep interval for the actuator is 60 milliseconds. This proved to be reasonable. It increases latency by 60 milliseconds in some cases, but that's not terrible. If it then it checks when it wakes up, it checks the IMU motion flag. If motion was not detected, it goes back to light sleep. If motion is detected, it listens for wireless messages for 25 milliseconds. And again, this interval was optimized to ensure that messages are received. Any shorter intervals caused problems with receiving messages, but increasing this interval didn't improve latency, but it increased energy use, so it didn't make sense to increase it. During this interval, if the actuator receives a message, it executes the message and it goes back to sleep. If it doesn't receive any messages, it just goes back to sleep. Okay, so with this implementation, I tested the battery life. I measured the current using a regulated power supply at the rated voltage of the battery. And then I use the current at the voltage to calculate power use and estimate battery life. So the shifter is the most constrained in terms of energy budget. And as you can see, battery life during riding is decent, between 6 and 10 hours roughly, which is should be plenty for a normal bike ride. But the number of shifts is a bit limited. So if someone is aggressive with shifting, if they shift very frequently, it could be a limiting factor. Sometimes below 400 shifts per battery charge. A standby or deep sleep battery life is still not great, between 40 and 60 hours. So overnight it loses about 50% of the battery. So this could be improved by using the physical power switches that the shifter includes. Uh, The actuator, on the other hand, is a bit more complex and has more modes. So when it's not moving, it still uses a good amount of energy, around 40 milliamps, and this is because not all the components are software controlled. So for example, power supplies or drivers cannot be turned off completely when it goes to sleep, so it stays relatively high. But the battery is much larger for the actuator. It's 3,500 milliamp hours. So although the current is higher, battery life is better than for the shifter. When it's moving and listening for messages, which is not that relevant, it's a bit lower. It's about half of that battery life. But what is more important is when it's moving and shifting. And when it's shifting, the motor uses a lot of current. So um, it it really depends on the duty cycle, the battery life, but the number of shifts is very reasonable, like about 10,000 shifts. That's very adequate for a normal bike ride. So that means that a combination of standby and shifting that would be characteristic of a bike ride, about one shift per minute, would have a very good battery life. So really the shifter is the limiting factor in this case. Um, Another factor that is very important for this system is responsiveness, so the communication latency and also gear change, delays. So I measured multiple of these processes. For example, waking up the actuator, and when I say wake up, it's just going from light sleep to a fully active, is very fast because it's not completely off. It's less than 1 milliseconds, but it only wakes up after the 60 millisecond interval, sleep interval. So the real latency issue is the sleep interval, not waking up. Waking up the shifter takes more time because it goes to deep sleep and it needs to run all the initial setup, but it takes about 17 milliseconds, which is very reasonable. Command delivery over the wireless protocol over ESP now, including resends that sometimes are necessary because the peer is asleep. Sometimes it takes 40 milliseconds, but sometimes it takes much longer, and this is basically because it needs to wait until the peer wakes up. But the real issue with the responsiveness is the gear in the motor. The motor proved to be not strong enough for this application, so gear changes sometimes take 300 milliseconds, but sometimes they take 800 milliseconds, and this is basically because shifting up is against the spring, and shifting down is with the spring. So the spring helps the gear change, so it can go faster. So the complete process can take between 0.4 and 1 second. This is a very big range, but really the communication latency and the wake up latency are not really the issue. The issue is the motor. So just including a stronger motor would improve the responsiveness more than the energy management, changing the energy management strategies. Okay, so in conclusion, the proof of concept works. This is not ready for real world use. Especially the mechanical systems need more work to meet real world requirements, but the electronic control units prove to be capable of executing all the required tasks. The communication protocols, position sensing, control algorithms, energy management strategies, pairing routines, and user interface provide most of the functionality that the expensive intellectual property protected products offer. But just using off-the-shelf components and open source frameworks. So the objective was met. And let's watch this short video that's also attached. So that one is the actuator. And on the hand, there's the controller with the spring. And you can see how it changes gears, and then the screen shows the new gear. Thank you.